Okay, so we are going to discuss synthetic method for the synthesis of metal organic framework. Metal organic framework is a type of coordination polymer. It is also inorganic polymer, but in this case, we have the combination between inorganic and organic moieties. It is uh, organic ligand and inorganic metal as the center. And the synthetic method consists of this one. They are prepared by self-assembly. Now I am introducing you with something called self-assembly. The assembly of this material without control of us. Yeah, as the researchers, we cannot control the how the product will be. For example, you will have maybe this one, and also you also maybe will have the product like this one. So for these two cases, we cannot control by ourselves, but it is controlled by themselves, by metal and ligand, how they behave, what will they make after combination of metal, iron, and organic ligand. It will depends on them. We cannot control by ourselves, so that we can say that it is controlled by self-assembly method. And then for example, I have two examples here. We have the same precursors here. We have silver, iron, and organic ligand. And the difference here is only about the pressure, the temperature you are working. For example, the first one, it is conducted in ambient temperature, and you get this compound one, this one, and this is the formula. It's not so clear, I'm sorry, but this is the new compound, and it is different with the second compound here. In the second compound, you perform this reaction at ambient pressure, but by increase by increasing the temperature until 90 degrees. It is at ambient pressure and temperature, and the second one at the higher temperature. What you get here is difference from the previous one. The complex one was obtained at ambient temperature, and it is different with the compound 2, which is obtained in the higher temperature. So these two cannot be controlled by us. We do not understand how they prefer to form the first compound in ambient temperature, and how and why these precursors form this second compound at higher temperature. It is regulated and dictated by self-assembly method. And then involving crystallization of metal salts with a ligand. Yeah. Now we are making compounds. We are preparing new compounds, and we want to characterize. For example, this is the product. Our product. We cannot get the absolute structure, the actual structure of our compound without doing characterization. Characterization mostly conducted by using X-ray diffraction method, and the material for being able to be measured by our XRD machine is only in the form of crystal. So crystal is very important. So if you want to react silver ion with the ligands, you must make sure that your product is in the form of crystal. So if it is in crystal, then you will be able to conduct XRD measurement, and then you will get the actual or absolute structure of your product. But if you only get maybe powder, you get gel, you get uh, polycrystalline maybe, or something like that, you will not be able to do X-ray measurements, especially single crystal X-ray measurements. Then you will not be able also to deduct or get the actual structure of your product. So in summary, we have to get the crystal of your product. We have to get the product in the form of crystalline, yeah, the crystalline form, not amorphous form. not liquids. Everything must be in solid crystalline, so that we can do characterization or structure determination. And then mechanism of crystal engineering and molecular self-assembly are relevant. Now I'm introducing you with something called crystal engineering. Crystal engineering, maybe we know engineering when we construct building, maybe we design a city. It is about engineering. And our friends in Faculty of Engineering, they are engineer and they can make huge high building, yeah, high buildings. But as chemists, we are chemists. We can also be engineer. We are not only chemists or scientists, but we can also be an engineer for like our friends in the Faculty of Engineering. What we are going to build, if our friends in the Faculty of Engineering, Civil Engineering or Architecture, they form buildings for towers, for houses and many things. But we will also construct building, but it is in the form of molecule like this one, atoms, ions, ligand, and like this one. This is also the building, but in the form of compound or complex compound or coordination compound, or our case, it is now in the form of metal organic framework. So there are many types, there are many forms of buildings of our MOF. For this is the example. We have MOF 74, it is like this, and it is MOF 5, it is a KUST1, it is like this one, and MIL 101, ZIF 8, and PCM 8014. These are the buildings of our MOF. And as an engineer, we can also construct and develop this type of building like our friends in Faculty of Engineering built the house or high buildings, apartments, towers, and so on. So crystal engineering is also a field in chemistry. What will they do? They will construct, build, develop the buildings of material. For example, our coordination polymer, and these are the examples of what they have done so far as crystal engineer. Basically, there's a method to use to grow any crystal. For example, soften layering, slow diffusion, slow evaporation, and slow cooling. These are the way of growing crystal. So the topic now here, we can only be able to determine the structure. We have product, maybe it is in this form, or in this one, these buildings, this structure. We can only be able to get the structure only if we are able to grow the product in the form of crystal. So the product must be in the crystalline form, and so you have to be able to grow the crystal. You get the product after adding your precursor. For example, you have metal salts, and then you add organic ligands, then you mix them and you weight them. Then finally, you must be able to get crystals. And if you are able to get the crystals, then you can go to X-ray machine, do the X-ray determination of the structure, get the structure of your compounds. Yeah. And for doing this, this is the conventional method. This is the conventional method. So everybody can do this by using gaseous available in our laboratory. For example, solvent layering, slow diffusion, slow evaporation, and slow cooling. This is the way how you grow the crystal. This is the way how you grow the crystals from its solution. Yeah. And the second one, to in this about method for mold preparation. Yeah, yeah. You have metal salts, you have ligand, and you want to make it mold. So there are many ways. And this topic is included in inorganic synthesis. Inorganic synthesis. Yeah, in the lecture called inorganic synthesis, you will discuss and study there are many ways to conduct reaction, chemical reaction, or especially inorganic reactions. For example, these are our inorganic reaction between metal, salts, and ligand, and we want them to form our product MOF. And for this case, you have many ways to do. If one failed, you can move to the next one. What are they? For example, you can do it by normal mixing. Yeah, you make one solution containing metal salts and the second class was second class containing ligand. Then you mix them together, you wait, and then you get product. It is the easiest way. It is the conventional way. But if it fails, then you can go and try the next ways. For example, we have sulfur thermal method, and it is very well known in organic synthesis, in preparation of metal organic framework, sulfur thermal method. And then if you fail, you can also try other ways. For example, microwave inorganic synthesis. You use microwave for this one. For this case, you put your sample. For example, this is your beaker glass. You put them together in one beaker glass, then you put it in a microwave machine. Maybe domestic microwave is also possible. And then you irradiate for a few minutes. Then you take it out from this microwave machine. Then you will get the product hopefully. And if you get the crystal, you can do the crystal structure determination. And if it fails, you can also try other methods. For example, ionothermal. This is you use ionic liquid as the solvent. And if it fails, you can also try electrochemical method. You have to do electrochemistry here. You have you have to prepare your electrode, your battery to perform electrochemistry, electrochemical synthesis. And also you can also use mechanical method, just combining them together. For example, take this salt, take the ligands powder, and then mix them together, and it is called mechanochemical. If you are lucky, then you will get crystals. If you get crystal, then you can do crystal structure determination and obtain the structure of your product, of your MOFs. And also possible to use sonochemistry, sonochemical method. You use ultrasonic. Maybe you can use also ultrasonic cleaner. You use ultrasonic cleaner for cleaning your glassware so far, but you have also, for your information, you also need to know that this ultrasonic cleaner can also be used to aid, assist the chemical synthesis. For example, you want to make MOF, you can use sonochemical method, ultrasonic sonication method. By using ultrasonic, you can do or make synthetic method for making MOF material. So these are the example of how the scientists make MOF. If they fail in one way, they will try other ways. And there are many ways used by inorganic synthesis experts so far. And these are the few examples of the ways they have done so far. And if they got product, they can also do crystal growing activity. Yeah, you get product here, maybe it is still in the solution form, and now your task, this is number one, this is number two actually, and number two, we are going to grow the crystal. Maybe your product here is still in the form of solution. And I'm sorry, there's some noise. Hmm? Hmm? What is it? Sorry, sorry. What is it? Okay, then we can continue. Because the main method of characterization of coordination polymer is X-ray crystallography, growing crystal of sufficient size and quality is very important. So our aim now is getting good crystal. Yeah, good crystal. Okay, now you can see here. This is the scheme. Yeah, yeah, yeah. This is your crystal. Yeah, in the beginning, actually, what you did is you want to add metal salts plus ligand, and you will get product metal organic perbrok as your product. But maybe your MOF is still in the form of uh, solution. What you are going to do, you have to be able to make them crystal. Yeah, this is a crystal. So your MOF material must be in the form of crystal. And if you see in your glass walls, in your bigger glass, you must see the crystals like this. These are the crystal, the products, and these are the product. Maybe yeah, it is under a microscope, and it is under your eyes. Yeah, like eyes. It should be like this one. You can see many crystal here, and if you enlarge them, it should be like this one. And this is the crystal we expect. We have to be able to get crystal like this one, and we take one of them. For example, I want to take this one and then bring it to X-ray machine. Yeah, X-ray machine is here. X-ray machine is our monitor here. So there should be X-ray machine here. And you put your crystal in the sample holder in the X-ray machine, and you irradiate with X-rays. Then you will get diffraction pattern, and then you have to do some refinements, computational computation, and programming in your computer, for example, many programs. Yeah, and to what, to get the electron density map, and then from here you will be able to get the atomic model of your sample. For example, this crystal, you can see the internal structure of the crystal. This is this example. For example, this is our biochemical material, maybe uh, DNA or protein, uh, and these are refinement. These are called refinement method. Yeah, refinement method. Yeah, from the diffraction pattern by X-ray machine, and to get this atomic model, either as model like our protein, and also in the form of atom. Yeah, how atom connected together, as I showed you before in the previous slides about some pictures, images of MOF materials. And these are only conducted in by using computers. So this is the man. He is doing refinements. He want he got this X-ray diffraction pattern from his crystals from X-ray machine, and he do the refinement, the activity of getting structure of this diffraction pattern. And there is software computer about this. There are many software computers how to do refine method, and he is doing this refinement, and finally he got this image of your crystal. And also for our case, we will be able to get the images of our MOFs material we have synthesized. Okay, then what we are, yeah, this is the process of crystal growth. Yeah, this is your bucket glass, and you have already put your metal salt. You add metal salt here, maybe metal plus, yeah, and you also add organic ligand, and then you also add solvent, yeah, solvent, maybe water and organic solvents, up to you. And then uh, After adding all of them together, maybe by simple mixing, then you have to wait. You have to wait. And if you are lucky, you will be able to get more materials in the form of crystalline one. The crystal will grow slowly. Maybe it takes 1 day or a few hours or 1 week or 1 month until 3 months to wait for the crystals. Yeah, and this is the photo showing you the process of crystal growth. Yeah, from its solution to this crystalline form, as you see here. This is the way of crystal growth. The way of crystal growth. And you take the crystal after it grows in the sufficient size. You take one, then bring it to the X-ray machine, do X-ray determination, X-ray irradiation to your sample, your crystal. Then you will get the X-ray diffraction pattern and do the refinement by using computer. Then you will get the structure of your crystal. Okay. Okay. Now we are going to do what we are going to do is how we are going to grow crystal. How we are going to grow your crystal. Uh, the first one, yeah. For example, this one, I have already add metal ion here, and also add ligand here, organic ligand, and also I also already add solvent. Solvent is already added here, and I now have solution of my product. Let's say we are successful in making MOF material, but the MOF is still in the solution phase like this one. There is no crystal here. So now we are going to tell you how you will be able to grow or get crystals from the solution of your product. Let's say you are successful in making your product MOF material, and this the color of your solution is red now, and you are expected, you are supposed to grow crystals from your solution. So what you are going to do, you can do this one, solvent layering method or slow diffusion method. Slow diffusion method, maybe this is the second one. The simple one is just forget this one. Just leave it. You just you have this one, maybe you have your product here, and you have solution of your product here like this one. The simplest one is just leave it and let the solvent evaporate. Let the solvent evaporate. So the solvent will evaporate and your product will remain in your glassware, in your beker glass. And after evaporation of your solvent, the concentration will increase. The concentration will increase, the solubility will be reached, and then the crystal will grow here. This is called crystallization. Crystallization is conducted by using this way. Just let the solvent evaporate by opening this cap, yeah, this end of your glass. Then the solvent will evaporate, your solution will be saturated, and your crystal will grow here. Please take the crystal, bring to X-ray, and then get the structure. This is the most simple one. And if this one doesn't work, you can go to the second ways. I call the way of solvent layering or solvent slow diffusion. Slow diffusion method. So this is our product, solution of our MOF material or product. Then put it in this bigger glass. It is bigger than this one, and you also add solvent here, other solvents, but it is more volatile solvent, and your sample is not uh, soluble hardly soluble in this kind of solvent. So this second solvent, the volatile solvent, uh, your MOF doesn't like this solvent. It will not dissolve in this solvent. For this setup, you can see that this solvent will evaporate and it will go up, but this cap here, it cannot go out. So that how where will it go? It will go everywhere, including to your solution. It will go here, and what will happen? Your sample will be saturated. In this case, your sample is in the solution form. Your sample is soluble in this first solution, maybe water here. But if you add maybe organic solvent here, and your sample doesn't like organic solvent, or uh, be it will be crystallized or precipitated because it doesn't like the organic solvent, then it will grow crystal. Because why? Because your solvent will go here, your volatile solvent, organic solvent will go here, and it will mix with the, say, your water as a solvent. Then it will be like this one, and your sample now doesn't like the new solvents, and so that doesn't like mean it is not soluble in the solvent. And what will happen? It will be solidified, precipitated, and in this case, the precipitation is very good. It will grow crystal. Then you are able to grow the crystal from the solution. Yeah, this is the number two. Number two ways of growing crystals from the solution: solvent layering or solvent slow diffusion by using other type of volatile solvents at which your product, your sample is not soluble or poorly soluble in that solvent. Okay, then we can continue the second one, slow cooling method. Maybe I shall put number 3 here, slow cooling method. This is your product containing MOF materials, and what you are supposed to do is throwing crystals from this solution of your product. So what you do, you can take this glass containing your solution and bring it to maybe a refrigerator. Refrigerator, put it there, and then just wait maybe for few hours or few days, and then come back and see, open the refrigerator, and you will see that there is crystal in the bottom of your beker glass. Why? Because in the refrigerator temperature is very low, maybe 0 degrees, yeah, maybe 5 degrees, and this your ambient temperature is around 30 degrees. So that if we reduce, decrease the temperature, the solubility will be decreased. So this is the graph telling you about the relationship between temperature and solubility of any solids. Yeah, mostly like this one. If you increase this temperature, the solubility will increase. Yeah, temperature increase, temperature increases, solubility also increases. But if you decrease the temperature, you go to the left, then what you see here, they also the decrease in solubility. For example, now we are here, it is maybe around here. Yeah, it is the current temperature, maybe 30 degrees Celsius. You have this one, this solubility high. Then if you decrease the temperature, maybe around 5 degrees Celsius, maybe, so that your solubility also decrease. What is solubility? Solubility is the maximum amount of sample you can dissolve in a solvent. Yeah, it is the definition of solubility. If it is more than the solubility, it will be precipitate. It will precipitate. And this also happens in our slow cooling method. you decrease the temperature, solubility will also decrease, and the solution will start to precipitate. And we are lucky because the precipitate is not in the form of powder here, but in the form of crystal. So this is what we expect. And if you are lucky, we are able to get good crystal here. And if it is sufficient in size and quality, we will be able to determine the structure of this crystal, the product. And we will get the structure and we are finished. Yeah, we get what we want. And then number 4, slow evaporation method. Slow evaporation method. I think it is similar with the number 1, evaporation. Evaporation. But in this case, we will make it slow. The evaporation should be slow because we want to grow good crystal. If the evaporation is very fast, let's say I open this one, there is no cover here, there is no cap here, then all the solvent would be uh, freely evaporate. Yeah, everything will evaporate without a hindrance. Without hindrance here, there's no cap, then it will evaporate fast. But this is not good for growing good crystal because crystal to grow needs time. Because you know what crystal is. Crystal is the collection of few particles and they are arranged in an ordered way. Yeah, they are very well ordered, very well arranged, very well ordered. It is the definition of crystals. So to make it ordered, you need time, of course. Everybody, even human being, for example, we are our softwares also need time to arrange our sources to be in row, one row. For example, if we have ceremony, for example, and student ceremony, we have to be in the yard in your campus, and we are supposed to make rows of students, and we need time to do so. We cannot make a good row, good line of us consisting of many students in short time. It isn't possible. We need maybe 5 minutes, 10 minutes, maybe 30 minutes to make a well arrangement of our surface. This also happen in this material, in these particles. They need time to arrange themselves in an ordered way. If they can order themselves in a good way, then it is crystal. We call that crystal. So this is the purpose of making it slow, making the process slow. How we make them slow? By covering this one and only making some slits here, some holes here. What for? To slow the evaporation. And if so, then we expect that we will have crystal. We are supposed to get crystal here by doing slow evaporation. For this case, if I just uncover the cover here, there is no cover here, then what will we get? Yeah, we'll get product also, but not in the form of crystals. It will be in the form of powder. There will be powder here, precipitate here, and if it is in the form of precipitate, it is no use in X-ray machine. X-ray machine cannot detect your sample in the form of powder. I mean here, single crystal X-ray diffraction, yeah, X-ray diffractometer for determining the structure of your product. So if it is in the form of powder, single crystal X-ray doesn't work. You cannot determine your crystal structure. But if it is in this case, you are able to determine the structure because your machine X-ray diffractometer needs this good and sufficient in size and quality sample crystal. Okay, this is how we do the slow evaporation method, and also this can also be done by using this, what is it, yeah, something like this one, yeah, NMR tube. It's called NMR tube. NMR tube. It's an NMR tube. You put the sample here and make it like this. You have needle here, and then this evaporation will take time. Yeah, then it is good because your crystal will grow here. Crystal, crystal, crystal. And if it's crystal, then it is good. You can do the crystal structure determination. Okay, so these are the example. We have discussed the MOF synthetic method. We have sulfothermal, hydrothermal, sonochemical, microwave, and so on. We also have studied the ways of growing crystal from its solution, by using slow evaporation, slow cooling, yeah, solvent evaporation, and solvent diffusion. These are the methods we have discussed so far in the ways of obtaining MOF material or MOF crystal. Now we are going to discuss the forces and bonding in metal organic framework. So I have told you we have we have many. We have our product. This our MOF. This is our MOF. Uh, this is example. You can see this is the ligand. The metal is here. Ligand metal, ligand metal. So the atoms are here. And what we are going to discuss now is what types of bonding and forces, yeah, uh, working on them so that they can maintain their structure like this. So the structure can be like this because there are many bondings and forces work on this structure. Yeah, for example, maybe covalent bonding between this one and this one, maybe hydrogen bonding between this one and this one, maybe pi-pi interaction between the benzene ring here, maybe many things, many types of bonding. So this crystal structure, the structure here, our bonding to be like this one needs other forces and bonding, other forces, chemical forces and chemical bonding. Maybe this one can be one, this one, and this one. These are determined by the type of metals, the type of ligands, also the type of forces and chemical bonding, yeah, on them. Now we are going to study what are the chemical forces and chemical bonding working on our MOF materials. This is the example. This is the force, the forces that determine the metal ligand complex interaction. So we have forces, we have bonding, forces and bonding. If we discuss bonding, it must be related with maybe three types of bonding. We have ionic bonding, we have covalent bonding, we have metallic bonding. These are the three types of chemical bonding we have learned so far. And also in chemistry, there is also chemical forces. This work between molecules, yeah, between molecules. Chemical bonding applies in molecules. Let's say you have chlorine gas, Cl2, Cl2. So you know that this one is covalent bonding. And we have molecule, we have a molecule Cl2, Cl2. So we can say that it is chemical bonding. It is covalent bonding between Cl and Cl. But you have many Cl, of course. We have many Cl2. We have many chlorine. We have many chlorine molecule. And there is interaction actually between one molecule with other molecules. Yeah, there are many interaction actually. For example, we have Cl2 here, and there is also Cl2 in its neighbor. And between these two Cl2, there is also interaction. and I call this one forces, intermolecular forces. Intermolecular forces, the forces acting between molecules. For example, we have molecule of CO2 here, Cl2 here, and there is interaction between this one and this one. They attract each other. There is attraction between these molecules, and we call this one intermolecular forces. And for this case, we can say the name of this forces is London dispersion forces. You can say that it is dispersion forces only, or London dispersion forces only. It's okay, but it is a type of intermolecular forces. Okay, these also intermolecular forces, intermolecular forces. And there are force in this case. There are there are four intermolecular forces here. Van der Waals forces, pi interaction, hydrogen bonding, and pi stabilization. Yeah, a bond bipolarized bond in addition to coordination bond formed between metal and ligand. Okay. In this one, you can also other type of intermolecular forces. For example, you have water, H2O. H2O, we have covalent bonding here, but between H2O molecules, from one molecule with other molecules, there is also interaction. If Cl2 has London dispersion forces interaction, for water, there is hydrogen bonding interaction. And this hydrogen bonding between O and H from other H2O molecule. It is also intermolecular process, and the name of the process is hydrogen bonding. Hydrogen bonding works in water molecule and also polar molecule with H, O, or N atoms on them. But this intermolecular process, like this percent process, only work for non-polar uh, covalent molecules. Yeah. And then what else? Let us discuss one by one. We will discuss later on. Let us see here. Here I'm introducing you with intermolecular and intramolecular forces. Uh, we have discussed covalent bond. Yeah, in SSR we have learned covalent bonds, ionic bonding, covalent bonding, and also metallic bonding. PBD, MOT, we have discussed so far. These are intermolecular forces. Yeah, forces within a molecule, and they are strong and very strong. We also have intermolecular forces. In this case, we have forces between molecules, one molecule with other molecules. So we have, for example, hydrogen bonding. We have the example of water in the previous slide. We have also dispersion forces. For example, we have Cl2 and Cl2 in the previous slide. And in addition with these two, there's also dipole-dipole interaction. Dipole-dipole and also ion-dipole interaction. These are the examples of intermolecular forces and also the relative strength of them. For example, hydrogen bonding is very strong compared with dispersion forces, but ion-dipole interaction is stronger, I think, uh, from hydrogen bonding, you see from this scale. And in between, we have dipole-dipole interaction. It is stronger than dispersion force, but less strong than H bonding or ion dipole interaction. So these are the chemical forces we have known so far. I hope this topic is already discussed in SSR, structure of inorganic compounds subject courses, and we apply this topic in our inorganic polymer. And this also uh, further examples, yeah, other examples of our intermolecular forces. For example, ion dipole already discussed, hydrogen bonding already discussed, dipole, ion dipole, ion induced dipole interaction, dipole induced dipole, and also dispersion forces. And these are the example. We have ion dipole, its ion is interacted interacting with dipole from other molecules. From one molecule, it is one dipole. It's also dipole from that molecule. There will be interaction. This ionic compound in the covalent compound, what it is polar, then there will be ion-induced dipole interaction or non-polar. And if it is dipole and the induced dipole can also be possible. For example, these are the example HCl with HCl and dispersion process. It is example fluorine and chlorine molecule. And these are the energy or the strength of interaction. The strongest is here, ion dipole, and then hydrogen bonding, dipole dipole, yeah, ion induced dipole, dipole induced dipole, and dispersion forces. This is the example of interaction. Okay. Now we will continue with this intermolecular forces tend to be weak with a long equilibrium distance bond length compared to covalent bonds. Yeah, we have discussed covalent bond is stronger than intermolecular force. Yeah, very weak. We have oxygen, strong, but this is very weak. There is interaction, but strength is very weak. Then pi-pi interaction. Pi-pi interaction between benzene rings. This also something called pi-pi interaction. We have benzene here. Benzene. We have double bond here. It is benzene ring. And you know that it is pi bond. Pi bond. Pi bond. Yeah. This sigma bond. Sigma. But for this double bond, it is called pi bond. Pi bond. And it is delocalized actually, so that you can write in this way. Just write circle inside, and this tell you that the electron here is delocalized. It will go around here, yeah, around the circle, so that we can also draw benzene in this way. There is a circle inside this hexagon of benzene. Now it is the cloud of electron here. You have one benzene, you have one cloud of electron here. And below this benzene molecule, there is also other benzene molecule. For example, I just write one here. This also the benzene molecule. And this also have electron cloud here. So we have now electron cloud here, electron cloud here. Yeah, electron cloud here, okay. This time they will interact. Why? Because the interaction of electron cloud, and this, how can they interact? Because it is a cloud actually. Cloud. Sometimes it can be positive, sometimes it can be negative pole. Yeah, and maybe something, yeah, like this one, it can be like this one. If can be this one, yeah. There are more electrons here. High density electron here, there will be negative. Less electron here, it will be positive. And this will happen in our ring, benzene ring. Sometimes it will be negative, sometimes it will be positive, positively charged. Yeah, but polarity, not so ionic like iron. Of course, it's an ion. It's only uh, instantaneous dipole maybe, and this also have like this one. Then what will happen? There will be interaction, of course, because maybe some negative part, some negative charge in this electron cloud, because less electron there, it will interact with these parts. Maybe there are more electron cloud here, and it will be negatively charged. Then we will have interaction, positive and negative, and this way, this is called pi-pi interaction. Yeah, between pi electrons in benzene rings. Benzene ring have pi electrons. They have much electron over there. Then there will be interaction between cloud of electron of one benzene ring with the other cloud of electron from the other benzene ring. And this is the interaction of pi-pi interaction. And the energy is around 5 until 10 kilojoule per mole. Not so strong, of course, but it plays a role in the form of metal organic framework. So this type of interaction energy also take part in the formation of the building of our MOF material. Okay, okay, okay. Then we can continue with the next one. Van der Waals forces. Van der Waals forces. Yeah, or dispersion forces. This simple atom, uh, nucleus here, and this electron cloud. But you have to know that electron cloud is not rigid. Sometimes it can be polarized to be like this one. It is not spheric. It is not spherical anymore. Now it is ellipsoid because they disturbs of the cloud. It can be like this one. Maybe now the nucleus is here. It means that this must be positively charged here, and the cloud of electrons are accumulated in this side. And then we can say that it is negatively charged. Of course, it is not permanent. It is only temporarily. So that we can say that it is spontaneous, instantaneous dipole. Temporarily, not to be permanent, but only for few seconds only. And then it will go back to its original spheric form, like this one. And its neighbors, yeah, for example, this one can also face the same situation. It can be negatively charged, it can be positively charged, it can be ellipsoid like this. And if this happen, if there is negatively charged over here and there is positively charged here, there must be electrostatic interaction between positive and negative. Then we'll have interaction between these two. We call this one van der Waals forces or dispersion forces. It is very weak actually. It is very weak also. And this is, yeah, I have, yeah, this is my metal organic framework actually. And this just tell you about there are many van der Waals forces working on this structure. Maybe here, maybe, uh, yeah, maybe here, yeah. Basically the interaction between one molecule with other molecules. They can interact each other even if their interaction is not so strong, but even although it is not so strong, but it will take part in determination of the structure of your complex of your metal organic framework. Okay, and it's also, yeah, pi-pi interaction. Also, the name is pi-pi stacking. Pi-pi interaction, pi-pi stacking we have discussed previous slide. Refers to attractive non-covalent interaction between aromatic rings since they contain pi bonds. We have discussed so far previously. For example, this is the sandwich type, T-shaped and parallel displaced, but basically you just pay attention to this uh, delocalized electrons in the ring here, there is the pi electrons, then there will be interaction between them. Yeah. Okay. And yeah, this is an example. Yeah. So this is our metal framework, framework, metal framework, and electrostatic interaction moves, yeah, interaction with absorbent and also interaction between your MOF with hydrogen bonding with water, but also possible here. Acid base interaction with your MOF's material, pi-pi interaction, hydrophobic interaction. Yes, yeah. Even your MOF materials can also interact with others. For example, solvents maybe you already have obtained your MOF materials, and there are many forces acting on this MOF material, maybe intermolecular forces and intramolecular forces. This work in your MOF material, but your MOF materials with others can also interact with others. Yeah, for example, it want to interact with water here, and if this happen because because of the hydrogen bonding interaction between the water with MOF, it is possible, and it can also be acid-base interaction between your MOF with other materials in the way of acid-base interaction, and also there can be adsorption of your MOF. Let's say your MOF is used as adsorbent and it is able to absorb, so let's say metal ions or anions, and the interaction is because of the electrostatic interaction between your MOF's material with the adsorbate in the form of ions. Either it is positive ions, cations, or negative ions or anions. And then we have pi effect or pi interaction. Yeah, you see here we have pi interaction. There are pi electron here, pi electron here. This pi interaction we have discussed before. And there can also be CH or alkyl pi interaction. There is pi electron here, and this alkyl here. So between alkyl and benzene ring, there is also interaction. It is because of the interaction between alkyl with the pi electrons here, and this also possible for the effect of pi or pi interaction for the molecules consisting of benzene ring. And also we have pi and natrium plus with benzene ring. There is also cation pi interaction, and pi stacking already discussed before between benzene ring and benzene ring, T-shape, L-shape, and so on. And also aromatic interaction. Yeah, we have different molecules here, different benzene here. It's only benzene here, but it is fluor, Rn here, benzene ring here, but the fluor atoms around here, around the benzene ring. Then since you have pi electrons here, then you will have pi interaction also. And this interaction between metal with your pi electrons, you have natrium ion will interact with these pi electrons in your benzene ring. And also water molecules can also interact with the pi electrons in your benzene ring. Okay, so these are the explanation for metal organic framework. We start from the definition of metal organic framework. We go to the application of metal organic framework we discussed last week, and also we discussed how to grow the single crystal of X-ray, which are sufficient enough to do crystal structure determination by using X-ray machine. And then we also discussed the forces, intermolecular forces especially, holding the structure of the unique structure of metal organic framework. I think this is my explanation for this topic about metal organic framework. And if you have something to ask about this topic, you can ask.